Hi, Math 8 students. So we're jumping further into our topic on Pythagorean theorem. I think the starter lesson on Pythagorean theorem went really well. The stuff I saw from you guys in terms of the Pearson Realize assignments and that Kahoot we did on our office hours, seems like you guys had this down really well. So we're going to move a little bit quicker for this one. As we jump into new content, I'm going to kind of slow down or speed up depending on where I see the class is at. And so this week we're going over converse of Pythagorean theorem, which I don't think will take a lot. We're going to kind of move through that part without a lot of getting into the weeds because I think you guys will get it pretty quick. And then we'll jump into some applications. So to start, just remember we got our Pythagorean theorem. Everything on these next two sections will be based on that. So remember we had our right triangle. So if we have a triangle with a single right angle, denoted by that little square symbol there, and we have sides A, B, and C, then we know that A squared plus B squared equals C squared. And from that, we know we can also have a triangle that isn't a right triangle. So you could have something like this, and you could have ABC triangles like this. But basically what 7-2, and we'll do kind of an example of it as well, but what 7-2 is going to go over is basically, how do you apply the opposite of that? So we could get like two side lengths of a triangle and we could find the third missing side of that triangle. But if we were given 3 bits of a triangle and we had no idea what this angle was here, if it was right or if it was something else, we could apply the converse. So converse, think we're going the opposite way. So converse, all it says is a triangle is a right triangle if and only if A squared plus B squared equals C squared. So a triangle is a right triangle if and only if you can apply the Pythagorean theorem. And later on in math, you'll figure out how to solve these triangles, something called the law of cosines, but that's for another day. Let's jump to the converse. So I'm going to take two triangles here, and we've got our converse. A triangle is a right triangle if and only if A squared plus B squared equals C squared. So here, we're kind of leaving these as unknown. Notice I haven't drawn my square here, so I have no idea if these are right or not. You could go in and kind of pixel analyze it, but based on the diagram, I have no idea. So instead of drawing a right triangle symbol, I'm going to draw a question mark on the angle that's like in question, whether it's a right triangle or not. So well, let's try applying this. So let's take two triangles. Let's say this one is a 3, 4, 5. We won't worry about units. We're just applying the concept. So let's say this one is a 3, 4, 5, and this one is, let's say, again, these are not to scale, but 7, 8, and 10. And we're going to ask the question, are these right triangles? So we have essentially this logical test here. So we have this converse of the Pythagorean theorem that says a triangle is a right triangle if and only if a squared plus b squared equals c squared. If this is not true, then we know it's not right. So what I'm going to do here is I'm just going to label these sides. Let's say this is A, this is B, and remember you can interchange A and B. A and B don't matter which one they are, as long as they're the two smaller sides. And C always has to be the hypotenuse. So we'll go ahead and apply this. So I can apply this a squared plus b squared equals c squared, and I'm going to see if that's true. So what I'm going to do is I'm going to write 3 squared, I'll write a squared plus b squared, which is 4 squared, and then I'll write a question mark, because we don't know if this is true or not. We only know if this is true if this is a right angle, but we don't know if this is a right angle. Does that equal 5 squared? And we'll go through and we'll sort of evaluate both hand sides, see if that's a true statement. So I'll go ahead and evaluate it. 3 squared, that'll just equal 9. 4 squared, that'll equal to 16. And we're going to ask the question again, does that equal to 5 squared, which simplifies down to 25. So I add the left-hand side together. We'll simplify that. 9 plus 16 gives me 25. And we get to a statement 25 equals 25. So what I have found here is that a squared plus b squared did indeed equal c squared. So we can go ahead and label this and say that is a right triangle. So now let's see what happens if I give you something that isn't right triangle. So you will find out soon this is not a right triangle, but I'm going to show you how to prove it. So again, we'll apply our converse. So we'll say we're just going to try the Pythagorean theorem equation, see if it holds true. If it doesn't, we know it's not right. So we'll try this again. We'll say A equals 7, B equals 8, and C is equal to 10. We'll plug those in. So we get 7 squared plus 8 squared. I'm moving a little faster because I think you guys are picking up on this concept. So we'll get 7 squared, which is 49. Feel free to slow down the video if you want to follow along with any of the calculations. Plus 64. And the Pythagorean theorem, better put my question mark there because I do not know if that's true. We're going to see if that holds true. So 49 plus 64. Let's see, 9 plus 4 is 3. Add the other two, and we get 113. And we can see that this is not a right triangle. So we say, no, this is not. And if you were to take maybe some toothpicks, say like toothpick that's length of 8, toothpick that's length of 7, toothpick that's length of 10, whatever units you're using, and you were to try to line them up, the only triangle you could really make would look something like this, with an oblique angle, an angle that's quite a bit greater than 90 degrees. So this one, not a right triangle. So you can see if the Pythagorean holds true, we say yes, a right triangle. If it doesn't hold true, we say no, it's not a right triangle. And I think that's about all we need for 7.2. So I'll post some practice on that, but we're going to jump now into applications. So we'll look at 7.3 now, right now. So I'm going to go example 1, then example 3, then example 2, just so you guys can cross-reference it with the book as well. I think that will be a little bit more of a beneficial way of going over this. So we're going to start now with applications. So we got Kayana, and she's using a kit to build a kite shown below. So the kit has 3 different lengths of wooden dowels, which are shown here. And then it says Kiana is to decide which piece of wood to use as a diagonal brace for the top or bottom of the kite. So let's look at what we have and what it means to have a diagonal brace. So we could kind of have a diagonal brace that goes across from this end kind of to this end. We could also brace from here to here across like that, or we could also put diagonal braces across here and kind of brace it across. And so let's look at this from kind of a 2-dimensional angle. So I'm going to erase those cross braces to start, but let's take just this little section here because we're going across here, and let's kind of just make this a 2-dimensional problem. So what I'm going to do is I'm going to take this rectangle here that has 4 right angles, and we're just going to draw it to the side, and I can just represent that as a box. So we got a box. Let me go ahead and change my colors really quick for that. Let's do a box like that. So I've got my box, and I'm kind of just taking this and just making it into a 2-dimensional problem. We'll carry over our right angles. And we got some information here. So we know that this is 21 inches. This is 28 inches. And we're trying to find a diagonal support. So if we draw that across, I'll draw that in a different color. Maybe put that in red. We're trying to find how long of a cross beam should we use across. And if you look at this, we have essentially created a right triangle. This one kind of juxtaposed or kind of crosses throughout, but this is a right angle here. So essentially what we've made is a right triangle with the dimensions 21 inches by 28 inches. And our hypotenuse here, since that's the one's opposite of the right angle, that's going to be our cross section. So all we need to do here to find our cross section length is solve for C. And we've got a formula to find that. So I know this is a right triangle, so the Pythagorean theorem must hold true. So A squared plus B squared is going to be equal to C squared. and I know what A and B are. So again, doesn't matter which one I plug into which. If I say A is 21 or A is 28, we'll just go ahead and plug them in. So I'll say A and B, but if you wanted to do A is 28, B is 21, you'd get the exact same solution. So go ahead and plug those in. So A is 21, so I'll go ahead and write 21 squared plus 28 squared equals my unknown C squared. And now we can just algebra this out. So nothing fancy here. We just go ahead and solve for C. So I'll evaluate 21 squared and 28 squared. So if you want to slow down and kind of do these calculations with me, you can. But 21 squared, we will get 441. 28 squared, we will get 784. And that will be equal to my C squared. And now we want to square root both sides, but let's simplify, combine these two like terms first. 441 plus 784, that will give us 1,225 is equal to C squared. And now, my last operation, I just got to undo my square. I can do that with a square root. This time I'm not going to worry about the plus or minus because I know the dowel rod is going to be a positive link. I don't need to worry about the plus or minus here. So I'll just take the positive solution, eliminate the negative solution right now. So let's take the square root of 1,225 and I get C is equal to 35. And let's put some units on there. A and B were in units of inches, so C is in units of inches. C is 35 inches. So we go back to our start of our problem. And I know, since these are right angles, that these cross sections that go across are going to be 35 inches. So I want to take this dowel rod, pop it right in as my support. All right, let's take a look at an example now where you need to apply the converse. So we're going to jump to example 3, and we'll jump back to example 2. So let's take the converse, but first let's see why. So we got Sandra. She's buying a triangular shelf to hang on the corner of her room, and she wants to know, will this shelf fit a 90-degree corner? So we look at the corner piece, and you know, kind of triangular shelves, you got like a wall here, and like right on the edge of the wall, where it kind of takes a 90-degree angle, she's going to kind of fit it up against the wall. So she wants to figure out if that will work. So essentially what she can do here is she's got a triangle. We can call this A, we can call this B, we can call this C. But we don't know if it's a right triangle. And she wants to know if it fits right on the edge of a wall or at a 90-degree angle. So we don't know if this is 90 degrees. So let's apply the converse then. So triangle is a right triangle if and only if A squared plus B squared equals C squared. So we're going to ask the question, in this triangle, and I can basically write it from a top-down view. We got 18, 24, and 30. Does A squared plus B squared equal C squared? If it does, we know it's a right triangle. So go ahead, we'll solve this, we'll write this problem out and solve it. So I want to know if A squared plus B squared equals C squared. So I'll go ahead and write that out. I want to know if 18 squared plus 24 squared is equal to 30 squared. So I'm just going to go ahead and evaluate this out. We'll see if the left-hand side is just like a check step. We're just seeing if the left-hand side equals the right-hand side. So I'll take 18 squared. That will give me 324. We'll take 24 squared. That is equal to 576. And we'll see if it's equal to 30 squared, which 30 squared evaluates down to 900. So right-hand side pretty much as simplified as we can get. So we'll just combine 324 and 576. We do that, pop it into our calculator or do it in our head. We do get 900. So what we found here is that A squared plus B squared does equal C squared. And that tells you that it's a right triangle, because if and only if A squared equals B squared equals C squared, it's right, which means we can confirm this is a right angle. So therefore, if it's a right angle, it will fit in a 90-degree corner. And we can say, yes, this will work. So there's an application of the converse. So I want to show you one more example when things get a little bit more to track. So now we're going to look at what happens when I have to apply the Pythagorean theorem in 3 dimensions. So we're going to take a look at example 2, and I'll bring this up so we can see the entire diagram. So first, let's kind of sort through how do we kind of attack this problem. So let's read it first, see what we got to do. So Alex has a column aquarium with a rectangular base that has a height of 66 inches. So immediately we know that each one of these height columns is 66 inches. And we'll go ahead and label one of them in case we need to refer back. We also know that this back here is 66, but I think we've done our due diligence here. We also know, let's keep reading, a length of 10 inches. So we'll go ahead. We could mix and match this, but let's label these as, oops, it's just that one. So we know that that is 10 inches. We know that that is 10 inches, and we also know that that is 10 inches. And if you mismatch or switch the length and the width, wouldn't really matter. And next, we've got a width of 14.5. So let's go ahead and label that. We've got a width of 14.5. And now, what is the longest piece of cholla wood? I'm not even sure what cholla wood is, but it's probably this right here. Would fit in his tank. So if you ever kind of try to like finagle something into a rectangular shape, you kind of know the best way to fit it in is if we go across like this, from kind of like one corner to the side here up to the other, and that's kind of the longest piece. If you ever just like messed around with this in real life, I think you'll find that holds true. And so essentially what we can do is we could create a triangle that looks like this, where I've got 66, but here I don't know this length. And I could eventually, hopefully, find this length. So we can see here is I could make this triangle here, but I do not know this length. So we've got to try something else, or we have to take a step beforehand. So I'm going to go ahead, take this length, and forget about it for now. So we won't worry about that for now. Instead, what we're going to go through is we're going to see if we can figure out what this length is. So we might have a couple steps for this problem. So essentially, if I look at this, I know this is rectangular. So I know that all of these are right angles, kind of like I did in example 1. And I've actually got enough information here to solve for this length. So I could look at the bottom of this, essentially aquarium. And if I looked like down this column from the top down, I would essentially see this square, where I've got 10 inches across and 14.5 here. And since all of these are right angles, I essentially have a right triangle here. So I could say that essentially I'm trying to solve for the hypotenuse to get this length of a 10 by 14.5 triangle with the hypotenuse unknown. So we'll just apply the Pythagorean theorem here, just an a squared plus b squared equals c squared problem. So this just becomes 10 squared plus 14.5 squared equals our unknown quantity squared. And we just go to town on it just like we did the previous problem. So go ahead and evaluate all these. I'll be kind of moving along a little quickly, but if you want to pause the video, follow along calculation wise, feel free to do so. But we got 10 squared is equal to 100 plus 14.5 squared. That'll be equal to 210.25, and that'll be equal to c squared. So just like we did before, we'll simplify the left-hand side. 100 plus 210.25. That's one that kind of the digits line up, so you can just do it in your head pretty easily. Equals c squared. And again, we'll square root both sides. We know the context of the problem, so we're not going to take the negative solution, only the positive. 310.25 squared of that is 17.18 inches. And that is equal to c. And let me just double check my units, make sure we were in units of inches. Yes, we were. So what I can do now is This is no longer an unknown. That length there is 17.18 inches. And we can go back to that triangle that I was originally investigating, is that I essentially have a triangle across here. That's my hypotenuse, that red line. Let's go ahead and label it in red just to stay consistent on that. And then I have these two purple lines. And I also know, since this is rectangular, this is another right angle. So I actually have another triangle I could solve. So we've gone from the two dimensions of this to be able to apply this hypotenuse to this triangle here. So I'm going to go ahead, take this triangle here. We'll split it off into two dimensions again. So I've got a triangle here that is right with a base of 17.18 inches and a height of 66. And now I just need to solve for my new c, this distance across here. So again, same applications here. We got a squared plus b squared equals c squared, 17.18 squared plus 66 squared. Don't need to put a question mark over my equal sign because I know it's a right triangle, is equal to c squared, that length that my wood is going to have to span across. So 17.18 squared, that will be equal to approximately 292.41. I'm okay with approximations right here. We're fitting a piece of wood into an aquarium, not shooting a rocket into space. Plus 66 squared, that is equal to 4,356. And that will be equal to c squared. So we'll simplify that out. That gives me 4,648.41. That is equal to c squared. And now we just do our final step that always occurs in these problems. Square root both sides. Again, we're only going to worry about the positive solution, not the negative, because we know this is a positive quantity given the context. Simplify that down, and we get c is equal to 68.18. And let's put the units on it now. They were all in units of inches, so we'll see 68.18 units across. And we'll go ahead and just label this. So that will tell us how long the cholla wood will have to be to fit across. So we can even just label that really quick. 68.18 inches. So again, we kind of covered the converse. We covered some applying to 2 dimensions, applying just the converse itself to another 2 dimensions, and applying 3 dimensions. So if this was helpful, let me know. And then also, if you have any questions on this, anything that was confusing, make sure you write down your questions and bring them to the office hours we have on Wednesday. So hope to see you all there. Take care. It's Mr. Merrifield signing off.